So here we're back with our relativistic Euler-Cromer method. It works the same way as the normal Euler-Cromer method. We just have to introduce this relativistic factor. Again, it's this factor that keeps the red particle's velocity from getting any faster than c, the speed of light. For our green non-relativistic particle, we don't have that relativity factor, so this is just the regular non-relativistic Euler-Cromer method. The difference this time around is that we're implementing a spring force. So the spring force, as usual, is negative, so that it always points in the backward direction from where the spring is trying to go, times the spring stiffness, so the stiffer the spring is, the stronger the force is, and then times the object's position, so the farther away it gets, the stronger this force pulls backward. We're going to start out with a pretty weak spring stiffness to begin with, just 0.01. When we hit Control 2, we're going to see the type of behavior we've expected to see before. These things are going to oscillate back and forth. You notice they're on pretty much the same trajectory, but you notice that the red one, the relativistic particle, is lagging behind the green one. Let's take a look at why that is by looking at their graphs. So here we've got the position versus time graph. Again, red is relativistic, green is non-relativistic. And you see they go through the same amplitude change, or excuse me, they go between the same amplitude, so from -5 to 5. So we've still got conservation of energy going on. The difference is, though, in their period. So the red one has a little bit longer period than the green one, so it's lagging behind it. If we take a look at the velocity graph, we can see why that's happening. You notice that the velocity graph is starting to get a little bit broader as we get closer to extreme speeds. That's because we're getting closer to that speed of light of 1. So in this case, for simplicity, we set the speed of light c equal to 1. And as we get to a speed of about a half, the speed has to start to level out because it can't get too close to that speed of light. The green curve is under no such restriction, so we get a traditional sine curve. But this red one is a little bit of a squashed sine curve, as it were. Now, it's kind of hard to see that effect here because it's a relatively weak spring. If we make our spring stronger, so let's triple the spring stiffness, we're going to see that effect pronounced even more. So again, they're both moving faster now because a stronger spring has a shorter oscillation period. Here we've got our position versus time graph. Again, the red object, because of its relativistic nature, is lagging behind the green one. Here we can really see that speed limit come into play. As we get too close to the speed of light, this curve, this red one, has to flatten out. So this is no longer a traditional sine curve. This is a distorted or a squashed time curve because it can't get up to +1. It can't get down to -1. Let's up the spring stiffness even more. Let's go up to 0.05. So this is 5 times the original strength that we had. Here we've got our particles zipping along. The red one definitely lagging behind the green one this time, again because of that speed limit. You can even see it can't get up to the same speed as the green one. Here we've got our position versus time graph, and so you can see on the red one, it's kind of becoming linear in the center. It doesn't have quite the same curvature as the green one, and we're going to see that show up here in the velocity versus time graph, where it's really starting to flatten out, right? So a flattened speed results in a linear position graph. So we're definitely getting close to that speed limit here. And in fact, you can see the green one's definitely not relativistic because it's exceeding the speed of light with every oscillation. So it's not hindered by that speed limit. So I thought a fun thing to do for the rest of this video would be to do a little experiment to try to figure out how these periods are being affected by the relativity here. So what I'm going to do is adjust this K value, and I've set up a spreadsheet here, and I'll make this available in a link in the description below along with the code, where we're going to record the spring stiffness and then the period of the non-relativistic harmonic oscillator. And let me just give myself a reminder, that's the green one. And for the relativistic harmonic oscillator period, that's the red one. In fact, let's even reinforce those with a green fill, there we go, and a red fill, just so I don't get myself confused. And I don't want to have to measure these things on the graph, right? That's not the most fun thing to do in the world. So what we're going to do is have the computer tell us when they have completed one period. So let's see, where do they start out? They start out at -5. So let's do this. Let's have this thing spit out when the when one cycle is complete. We're going to have it spit out the period. So let's do this. So let's have if the relativity position dot x is, I'm always hesitant to do an equal sign. So let's do less than negative 4.9, because you never know if it's going to be 4.99999 and not count that as equal. And then we'll say, and let's have the time be greater than, let's see, I need it to be greater than a few time steps. Let's just say greater than the first like 5 dt, just to get that first little bit out of the way. Oh, actually, I have a better way to do this. The better way to do this would be to just do half the period and multiply it by 2. So let's actually ignore that. We'll just have this be greater than 4.9. And then we'll just take the time and we'll say print. Let's see, this one is which one's relativity? This is relativistic period. That is red. Equals, and that's going to be 2 times the time. So we're looking now for when it reaches the peak, not the trough. So when it goes from here, actually I want to go up to the position graph, don't I? Yeah, so when it goes from here to the peak, that's half of a period. We have to go back down to get the entire period, so we'll just multiply it by 2. Now, of course, I don't want it spitting that every single time, so I want to have a logical variable to say relative period. We'll start that out as false, and this is just, have you printed relativistic period yet? So we'll say, and not rel period, and then down here we'll say rel period equals true. And then I can do the same thing for the non-relativistic object. Copy and paste. Oops. Make that non-rel. And then I just have to copy this block. Copy and paste. Oops. And all my, oh goodness, all my rels need to become non-rels. Non-rel, non-rel, not non-rel. Wouldn't that be non-rel? This is going to be non-relativistic period. By the way, just a little bit of commentary. I sometimes hear people or textbooks, read textbooks that refer to relativistic mechanics and classical mechanics. I really don't like that distinction because to me, the opposite of classical mechanics is quantum mechanics. To me, this is relativistic classical mechanics. Sorry, just a little soapbox there. Let's see, non-rel, 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 non-rel. All right, so I should now just be able to get these to print out once, and I'm missing a right parentheses. Oh yeah, oops. I thought something looked funny on that line, but I couldn't quite put my finger on it, or the cursor on it. All right, so when these guys finish that, it should tell me the periods. There we go. So this was how much? This was a K value of 0.05, 0.05, and my green one was 26.28, and my red one is 32.32. Tell you what, let's be a little bit smarter about this. Let's grab this guy. There we go. And now all I have to do in this window, actually let's pop this out, I guess. Now all I got to do in this window is change my K value. All right, let's go back down to the smallest value we had before, 0.01. We'll scroll down, we'll wait for the period to appear. So I've got a 0. I need to go over here. 0.01, got a 58.8 and a 61.68. All right, let's do one more and then I'll probably put the rest of this video in fast motion. Let's go up to 0.0, let's go up to 0.03. Control 2. Nope, there we go. And I've got a 33.94 and a, oops, I need to go this thing first. 33.94 and 38.76. All right, I know it's not the most thrilling thing to watch me enter data for 10 minutes in a row, so I'm going to put the rest of this in fast motion and we will graph it at the end of the video. So here on this last one, you can definitely tell the difference between the green one that's a sine curve and the red one that's almost like a box wave or a square wave at this point. I think I've got enough data to graph this now, so let's grab all of these data lines here, and we'll go Insert Chart. And I don't know why the default is a line chart. We never want a line chart in physics. Always want a scatter plot. Okay. So again, it didn't give me the right colors I wanted. At least it gave me red as red. So let's see here. So the non-relativistic one, of course, has a shorter period always than the relativistic red one. So that's good. Now we know from the derivation of this problem, from the analytical solution, that for the non-relativistic harmonic oscillator, it should go like 1 over k to the 1/2 power, so k to the minus 1/2 power. So I should be able to place these on a log-log scale, let's see, and get a straight line out of it. So let's put the horizontal axis on a log scale, and we'll put the vertical axis on a log scale. I still owe you a video about using log scales. I am aware of that, and that one is coming. I've got it in the works. But basically, when you have a power law, when you have something like this blue curve that's supposed to be a power law, so k to the minus 1/2 power, you're supposed to get a straight line because the logs allow you to cancel out all that power law stuff to basically get a straight line. And it's bothering me calling that green. So let me just really quick turn this into green here. There we go, that's better. Now we've got green and red. And so you see, for the green one, we do get a straight line. So this is definitely obeying a power law. For the red one, we don't. So it's not even that it switches to a different power, it's that it breaks, the relativity breaks the power law relationship entirely. Now what that relationship is, I'm not sure. I haven't solved that problem in probably about 15 years. So I'm going to leave it up to you, the viewer, to figure out what this relationship is, either by looking it up or by deriving it yourself, or by playing around with these data till you get some kind of fit that works out well. Would love to see that. Next time we'll take our harmonic oscillators here and we'll start to have them oscillate in 3 dimensions. So I think that'll be a lot of fun. So thanks so much for watching. I will see you next time. Bye-bye.